Rafael, quando você quiser.
Boa tarde, pessoal. É uma grande honra ser o responsável pela apresentação do quinto encontro de Machine Learning, organizado pelo C2D em parceria com o Itaú Unibanco. E eu tenho aqui algumas informações iniciais que eu gostaria de apresentar a todos. Em primeiro lugar, o Centro de Ciência de Dados, também conhecido como C2D, ele foi criado a partir do interesse comum da Escola Politécnica da USP e do Banco Itaú Unibanco para o desenvolvimento de pesquisas de excelência e para a capacitação de pessoas. O objetivo principal é o de fomentar o ecossistema da área de machine learning do nosso país. O centro ele conta com um comitê de acompanhamento, também conhecido como CA, que executa decisões táticas e operacionais, e com o comitê executivo, também conhecido como CE, responsável pelas ações estratégicas do C2D. Os membros do nosso CE são o professor Antônio Mauro Saraiva, o professor Fábio Cosma e eu mesmo, Rodrigo Melo. Os membros do nosso CA são a professora Ana Helena Reale Costa, o professor Jorge Hadid Almeida Júnior, o professor Pedro Luiz Pisigatti Corrêa, o doutor Etienne Américo Cartolano Júnior e o mestre Jardel Trento Negrão. Eu gostaria de começar agradecendo tanto aos membros do CA quanto aos membros do CE por essa parceria que já vem de alguns anos. Gostaria muito de agradecer o ex-diretor da DED, da Diretoria Estratégica de Dados aqui no Itaú, o Estevão Lasanha, por ter fomentado e acreditado muito nessa parceria. Obviamente, gostaria de agradecer também o nosso atual diretor, CTO Moisés Nascimento, por dar continuidade e, inclusive, por oferecer aí expectativas de expansão até mesmo nessa relação. E gostaria muito de agradecer também ao nosso ex-Chief Data Scientist, professor Eduardo Rusca, que iniciou essa parceria e hoje alça novos voos. Gostaria também de agradecer ao Vitor Azeca, que é superintendente da área de Advanced Analytics dentro da Diretoria Estratégica de Dados, e principalmente por engajar as suas equipes nessa parceria que nós temos com a Universidade de São Paulo, com a Escola Politécnica da Universidade de São Paulo. Agradecer também ao Etienne Cartolano e ao Jardel Negrão pelo desenvolvimento e pela manutenção da parceria não só com o C2D e com a Escola Politécnica da Universidade de São Paulo, mas também por manterem a parceria com o Laboratório de Ciências da Computação e Inteligência Artificial do MIT, o CSAIL, cujos pesquisadores farão apresentações logo em seguida no dia de hoje. Nós teremos duas apresentações vindas de pessoas que são professor e uma colaboradora dentro do MIT. Ao final, nós teremos algumas divulgações sobre vagas no Itaú Unibanco, pessoal. Nesse momento, eu convido, então, o professor Pedro Luiz Pisigatti Corrêa, membro do CA do C2D, que irá apresentar o centro e detalhar um pouco melhor a sua função. Muito obrigado, professor Pedro. Boa tarde.
Eu gostaria de agradecer inicialmente ao Itaú, através do Rodrigo Melo, dessa oportunidade de parceria que nós temos com a Escola Politécnica, que gerou aí o Centro de Ciência dos Dados, inicialmente. Gostaria também de agradecer, continuando os agradecimentos, né, aos organizadores aqui do evento, né, ao Fábio Levi, professor doutor Fábio Levi, do Departamento de Engenharia de Computação, e ao Etienne Cartolano, responsáveis aí pela estruturação e organização do evento, né? Bom, eu também agradeço, né, à Escola Politécnica da Universidade de São Paulo, que proporcionou e está organizando o nosso evento aqui na Escola Politécnica. Bom, iniciando então, eu gostaria de falar um pouquinho sobre o C2D, o papel do C2D, e falar um pouquinho sobre a nossa Escola Politécnica, né? Bom, o objetivo do C2D, conforme foi dito pelo Dr. Rodrigo Melo, é desenvolver pesquisas de ponta e capacitar pessoas na área de ciência de dados, inteligência artificial e fomentando o ecossistema da área no país, né? Há 4 anos, basicamente, que nós iniciamos essa parceria com o objetivo de criar massa crítica, né, nessa área de ciência dos dados, que envolve análise e gestão de dados de maneira geral, isso para contribuir na formação de pessoas de excelência, né, formação de excelência nessa área. Próximo slide aqui. Bom, o C2D ele está situado na Escola Politécnica. A Escola Politécnica é uma das mais importantes escolas da América Latina na área de engenharia, né? E a escola tem por missão formar profissionais comprometidos com o desenvolvimento sustentável do país, com responsabilidades social, econômica e ambiental, né? Alguns dados sobre a Escola Politécnica: ela é composta por 15 departamentos de ensino e pesquisa, ela tem em torno de 5.000 alunos de graduação, em 15 diferentes cursos de graduação na área de engenharia, né? E em pós-graduação existem vários programas de pós-graduação, né, stricto sensu, tendo entre mestres e doutores, né, atualmente, né, cursando os nossos cursos de pós-graduação, os nossos programas, em torno de 1.500 alunos, né? A Escola Politécnica, ela está situada entre uma das melhores escolas do mundo, né, a 105ª escola em termos de ranking, né? É o maior centro de pós-graduação em engenharia do Brasil, considerando os vários programas de pós-graduação que nós temos hoje e a diversidade dos programas de pós-graduação stricto sensu em engenharia. Ela é uma das principais formadoras de empreendedores executivos do Brasil, né? Um dos exemplos um dos fundadores do Itaú, é formado na Escola Politécnica, né? E a USP, é que cedia a Escola Politécnica, né? A USP, atualmente, ela é responsável por 1/5 de toda a produção científica nacional, né? Então, o C2D, ele está situado na Escola Politécnica, que a Escola Politécnica é parte da USP, só para vocês entenderem o contexto do C2D. Excelente. Bom, conforme a gente comentou, o C2D ele está situado hoje fisicamente, né, na Escola Politécnica, né? Ele é um dos centros aqui da Escola Politécnica, no prédio da Engenharia Elétrica da Escola Politécnica, né? Então, aqui só um mapinha para vocês se localizarem, terem uma ideia mais ou menos onde está situado o C2D. O C2D tem uma concepção bem arrojada, né? Ele até difere do ponto de vista das construções na Escola Politécnica, né? A gente já foi concebido com esse objetivo de ter uma distinção do ponto de vista de inovação, né? Aqui é só a foto de entrada aqui do Centro de Ciência dos Dados, né? No Centro de Ciência dos Dados, os bolsistas, os alunos de mestrado e doutorados, os orientadores, eles têm um ambiente de interação, né? O laboratório já foi concebido dessa maneira, de tal forma que, nesse ambiente de colaboração, as pessoas possam trocar informação, possam trocar ideias, né? Infelizmente, a gente não está podendo nós não podemos estar lá fisicamente, atualmente, em função aí da Covid, mas esse é o ambiente físico de onde os pesquisadores desenvolvem seus projetos e estabelecem a colaboração com os demais, interação entre os demais pesquisadores, tá? Bom, a parceria com o Itaú e a Escola Politécnica, com ênfase na criação do C2D, iniciou em 2018, né? De lá para cá foram realizados 8 eventos de Machine Learning, né? Além disso, o C2D apoiou outros eventos, workshops na área de ciência dos dados, né? É importante ressaltar que a Escola Politécnica, ela é uma das pioneiras, né? Nessa área de ciência dos dados, né? Dentro da USP, do ponto de vista de realização de eventos. Desde 2015, a Escola Politécnica vem realizando eventos nessa área de ciência dos dados, né? E uma das linhas aí importantes aí com essa interação com o Itaú é o programa de bolsas Itaú chamado PBI, né? O programa o PBI, atualmente, né, ele apoia alunos de iniciação científica, né, e também apoia projetos de formatura na graduação. Na pós-graduação, apoia alunos de mestrado e doutorado, né, tendo formado um doutor, 14 mestres, 4 trabalhos de TCC, 6 trabalhos de IC, e, enfim, o C2D hoje já publicou 11 editais, né, de bolsas do programa de bolsas do Itaú. Existem várias linhas de pesquisa, né? Aqui eu coloquei as principais linhas de pesquisa que são desenvolvidas nos projetos, né? Desenvolvidas nas bolsas que nós temos, né? Nas pesquisas. É importante ressaltar que 50% dessas bolsas são com ênfase em demandas do Itaú e 50% são a temas de interesse da Escola Politécnica como um todo, né? Então, existe essa colaboração de temas, né? Então, essa abertura com relação a temas de pesquisa dos bolsistas dentro do PBI. Bom, nós temos alguns resultados, né? Nós estamos colocando alguns resultados aí em relação aos resultados gerados pelo programa, né? Foram publicados 34 artigos até agora em periódicos, 7 prêmios, né? Tem vários trabalhos aqui que a gente pode citar, trabalhos relacionados a agentes, a parte de agentes conversacionais para chatbot, balanceamento de trade-offs em sistemas de recomendação, sumarização automática de múltiplas opiniões com aprendizado por reforço, e Big Data Analytics, voltado para gestão de dados, gestão e análise de dados na bacia amazônica, né? Esses são exemplos de alguns projetos do PBI. Bom, aqui tem o site do PBI, vocês fiquem à vontade, todos vocês estão à vontade para submeter propostas e participarem do nosso programa, tá? E qualquer dúvida, por favor, entre em contato conosco. Obrigado, Rodrigo.
Muito obrigado, professor Pedro. Ótima apresentação, contextualização e muito obrigado pelos resultados, inclusive como representante do Itaú aqui hoje, tá? Eu gostaria agora de convidar o Dr. Etienne Cartolano Júnior, que vai nos apresentar um pouco mais sobre a parceria CISEI-MIT em conjunto com o Itaú Unibanco. É contigo, Etienne. Muito obrigado.
Obrigado, Rodrigo. Eu vou compartilhar. Boa tarde, pessoal. Eu vou compartilhar a tela rapidinho com vocês, só para a gente olhar um site juntos. E aí, deixa eu ver se eu consigo. Acho que todos devem estar olhando o site agora, né? Bom, pessoal, boa tarde.
Sim,
Bem-vindos a...
super claro aqui.
Obrigado, Mela. Pessoal, boa tarde, bem-vindos ao nosso quinto encontro, né? Como o Melo fez a apresentação inicial, essa é a quinta edição do encontro. E hoje é um encontro bem interessante, porque no encontro do C2D, nós temos convidados do MIT. E aí a minha missão aqui, eu, Etienne, né, sou funcionário, cientista de dados do Banco Itaú, mas também hoje sou estudante do MIT, no MBA do MIT, patrocinado pelo Banco Itaú. E a minha missão hoje é fazer essa conexão entre o MIT e o C2D. E o legal aqui é que a gente, quanto Banco Itaú, a gente tem uma parceria acadêmica tanto com a Escola Politécnica, mas também com o Laboratório de Inteligência Artificial e Ciência da Computação do MIT. E o CICEIO, como é conhecido no MIT, ele tem diversas iniciativas com diversas áreas da indústria, na qual ela convida a indústria para ir até o MIT, se reunir em um grupo de empresas e propor desafios para o MIT. E uma dessas iniciativas é a chamada Fintech at Scale. São iniciativas relacionadas ao mercado financeiro, tecnologia, obviamente, e os desafios que a gente, enquanto empresa, com outros parceiros que nós propusemos ao MIT, são muito relacionados ao que a gente já trata no Centro de Ciências de Dados da Poli e que é os nossos desafios dos dia a dia no banco, enquanto um banco, vamos dizer assim, na vanguarda da tecnologia. As principais áreas que a gente desenvolve com o MIT no CICEIO são em relação à análise de dados avançada, inteligência artificial, segurança cibernética é um assunto muito em voga. Nós, no Itaú, há décadas, nos preocupamos bastante com duas coisas, né? Privacidade e segurança dos nossos dados e das transações dos nossos clientes, e hoje esse assunto está em evidência, então esse é um assunto importante que a gente quer discutir tanto com a Poli como com o MIT. Algumas questões de políticas em relação ao mercado financeiro, reconhecimento de padrões, robótica, inclusive, e processamento de linguagem naturais, ou seja, atividades que nos ajudam, nos dão suporte a criar produtos melhores para os nossos clientes dentro do banco, tá? Como é que funciona essa parceria? Nós estamos agora no terceiro ano dessa parceria. O Banco Itaú é um dos membros fundadores dessa iniciativa no MIT. E hoje, o projeto conta com 15 projetos em curso, né? São 15 professores do MIT que resolvem desafios que essas empresas propõem para a iniciativa. E hoje nós convidamos duas projetos para vir apresentar aqui no C2D. Qual é o nosso objetivo? É convergir essas iniciativas acadêmicas para que elas ganhem muito mais sinergia nos seus trabalhos. Não necessariamente diretamente trabalhando juntos, mas na troca de experiências e de temas também. Eu vou deixar para o Rodrigo Mello apresentar os pesquisadores e os projetos, mas fica aqui o convite aos pesquisadores que estão nos assistindo, aos profissionais que estão nos assistindo, a conhecer a iniciativa do Fintech at Scale. Eu coloquei aqui o site, né? Vocês podem acessar por cicale.mit.edu. Lá vocês conseguem achar essa iniciativa. E se tiverem interesse em ver algum tema que vocês talvez queiram desenvolver, estando no Brasil, desenvolver dentro da Poli, será muito interessante até para tentar conectar esses dois grupos de pesquisa, tá? Eu fico também à disposição para quem tiver dúvidas sobre essa iniciativa e outras atividades dentro do Banco Itaú. Combinado, Melo? Você apresenta os nossos convidados?
Com toda certeza, Etienne. Muito obrigado.
Obrigado.
Now, just after this short introduction with Professor Pedro and also Dr. Etienne, now we have two talks. We are going to start with Professor Julian Shun. Professor Fabio Levi told me that that's okay. You can proceed with the sharing. Thank you very much for being with us. It's a great honor.
Yeah, thank you for the invitation. I'm very happy to have this opportunity to share my work with you today. Should I should I start now or wait until 3 p.m.? Either way is fine with me.
I think it's okay. I think you can start. You can proceed. Thank you.
Okay. Okay. Let me make this full screen. Okay. You can see my slides, right?
Yes, yes, it's great. Yeah.
Okay, great. All right. Well, yeah, thanks again for the invitation. So today I'm going to talk about our work on parallel index-based structural graph clustering and its approximation. This is joint work with my PhD student, Tom Zheng, and also my previous postdoc, Lakshman Duapala. We have a paper describing this topic that was published in SIGMOD just this past summer. So if you're interested in this, I encourage you to read the paper for more details. I'll also be mentioning some other graph-related projects that we've been working on at the end of this talk. But most of this talk is going to be focusing on this parallel graph clustering algorithm that we developed. Okay, so the goal of graph clustering is to find groups of vertices that are well connected internally and poorly connected externally. So on the right, we have an example of a graph here. We have vertices and then edges that connect different vertices, which model some type of relationship between the two vertices in some application. And each of the blobs of vertices with the same color correspond to a cluster here. And we see that there are a lot of edges going between vertices in the same cluster and many fewer edges going across vertices from different clusters. And this is sort of what we would like for a graph clustering result, at least intuitively. There are many applications of graph clustering. For example, it can be used to do community detection in social networks where you might want to find groups of people that have similar hobbies and live in the same area. Clustering is also used in networks that arise from bioinformatics, like protein networks, where you want to identify certain substructures of the graph that have biological significance. Clustering can also be used in financial networks, document clustering, and then applications of machine learning like semi-supervised learning and unsupervised learning. Although I told you intuitively what we would like for the result of graph clustering, there's actually no universally accepted definition for measuring the quality of clusters. And many different metrics have been proposed for measuring the quality, and different metrics have different advantages and disadvantages, and you would choose metrics based on your domain. But because there are so many metrics out there that people have proposed, there have also been hundreds of different graph clustering algorithms that have been developed in the literature. So today I'm not going to be talking about all of these different clustering algorithms and all of these different metrics that have been proposed, but I'm just going to focus on a specific graph clustering algorithm that has been pretty popular in the literature and has been shown to give good results in various applications. And this is called the SCAN algorithm. SCAN stands for structural clustering algorithm for networks. And this was developed by Xu et al. In 2007. In the SCAN algorithm, the similarity of vertices is based on the number of shared neighbors that they have. So two vertices that have a lot of common neighbors will be more similar to each other than two vertices that have very few common neighbors. And the goal of the SCAN algorithm is to find these dense areas in the graph which contain many similar vertices. And these dense areas are going to form clusters. So on the right-hand side, we have a small graph here with two clusters, the red one and the blue one. And we see that within each cluster, the vertices actually share a lot of common neighbors with each other. But if you look at vertices from different clusters, like this blue vertex and this red one, it looks like they don't actually have any common neighbors other than themselves. And that's why this edge here will separate the vertices into two different clusters. We also have this unlabeled vertex over here. This is actually an outlier. It doesn't naturally belong to any cluster, so we just don't assign it a cluster. One advantage of the scan algorithm is that it doesn't require you to know the number of clusters beforehand. The algorithm is going to automatically determine the right number of clusters based on the input parameters that you pass to the scan algorithm, which I'll talk more about shortly. And as I said, that scan algorithm can identify both clusters as well as outlier vertices. And the scan algorithm contains two user-defined parameters that will affect the cluster generation. So if you change these parameters, it will give you different clusters. But the parameters will basically give you clusters at different scales. So if you want large clusters, you can use a certain setting of the parameters, whereas if you want many smaller clusters, then you would use a different setting of the parameters. And playing around with these parameters allow you to explore clusters at different scales in your data set. However, because there are these two input parameters that you need to test out, existing algorithms are pretty expensive because every time you change these two parameters, you have to rerun the algorithm. Even if the scan algorithm is parallel, it still takes a lot of time because many times data scientists want to try out different parameters to see which parameters give them reasonable clusters. So to overcome this bottleneck in our work, we propose a parallel data structure that allows us to efficiently query for scan clusters under different parameters. So here we're creating this data structure just once. After we create this data structure, we can query for scan clusters under different settings of these parameters very quickly, much faster than existing algorithms that need to be rerun every time. And we show that our algorithm is efficient in both theory as well as in practice. So here's an outline of the rest of my talk. So first, I'll give the definition of scan as well as related terminology. And then I'll talk about an existing sequential index-based scan data structure that our parallel algorithm is based on. And then I'll talk about our new parallel data structure. Then I'll talk about how we can use approximation to speed up the construction of our data structure. Then I'll present some experimental results. And finally, I'll discuss several other graph projects that my group has been working on. Okay, so in the scan algorithm, as I said earlier, a pair of adjacent vertices is similar if they share many common neighbors. And the original scan algorithm uses the following similarity metric, which is called cosine similarity. So we're going to take two vertices U and V, and then we're going to take the neighborhoods of each of the vertices. So if I say n of U, that means I'm getting the set of all of the neighbors of U in the graph. And I'm also going to include U itself in this neighborhood set. This is somewhat different from the traditional convention of neighborhood, but I'm just going to include the vertex itself because it makes the discussion simpler. Okay, so this is the quantity that defines the similarity between vertices U and V. So in the numerator, we're just taking the intersection of the neighborhood sets of U and V. So we're counting the number of common neighbors that they have. And then on the denominator, we're taking the square root of the product of the neighborhood sizes of U and V. So here's an example where we're computing the similarity between vertices F and G. So first we need to figure out the size of the neighborhoods of each of F and G. So F has a neighborhood size of 4. E, G, and H are real neighbors, but F is also going to be considered a neighbor in our presentation. Similarly, the number of neighbors of G is also 4. And then the intersection of the neighborhood sets of of F and G is going to be 3. So H is a common neighbor of F and G. It forms a triangle with F and G. And then F and G themselves are also counted as common neighbors. So in the numerator, we have a value of 3. In the denominator, we have square root of 4 times 4, which is just 4. And therefore, the similarity between vertices F and G is 3 over 4, or 0.75. In our paper, we also consider other similarity functions besides cosine similarity. We also look at Jacquard similarity as well as weighted cosine similarity, but I'm not going to discuss them further in this presentation. The key ideas for our algorithm don't depend on the similarity function. So I mentioned that there are two user-selected parameters in the scan algorithm. So we're going to call these mu and epsilon. And then we're going to define a vertex to be a core vertex if it has at least mu neighbors that are epsilon similar to it. So here's an example where I picked mu to be 3 and epsilon to be 0.6. Now I need to compute the similarity between every pair of adjacent vertices. So here I'm just going to color code these edges. So the edge is going to be green if the similarity between the two vertices on the edge is at least 0.6, and then it's going to be red otherwise. So here we see that A and D, they have a similarity that's at least 0.6. You can actually verify this by plugging in the appropriate quantities in the equation that I talked about on the previous slide, but I'm not going to actually do the calculation here. Next, we need to find out which vertices are core vertices. And it turns out that these vertices that I've colored in blue are the core vertices. So each of these vertices have at least 3 neighbors that are 0.6 or greater similar to it. So let's take A, for example. A has 3 neighbors, A itself, B, and D. And by definition, A is 1 similar to itself. And then because it has 2 green edges that go to B and D respectively, it's also epsilon similar to B and D. So therefore, it satisfies this criteria of having at least 3 neighbors that are 0.6 similar or better. So A is a core vertex, and then you can similarly verify that the other blue vertices are core vertices. Now, if you look at vertex J here, it's not a core vertex because it only has 2 neighbors, J itself and G. And even though it's epsilon similar to G, it doesn't have enough neighbors to be a core vertex because we need 3 neighbors. Now the clusters in the graph are going to be defined by the connected components of the core vertices along with any other epsilon similar neighbors that they have. And in our example here, these are going to be the 2 clusters. So we have A, B, C, and D as 1 cluster. They're all core vertices and they're all connected to each other. The other cluster is F, G, H, and J. So F, G, and H are core vertices, and they're all connected to each other. But G has a epsilon similar neighbor J, although J is not a core vertex, but it's epsilon similar to a core vertex that is its neighbor. So we add J to the cluster that its core vertex neighbor belongs to. And we call J a border vertex. So any vertex that belongs to a cluster, but it's not a core vertex, is called a border vertex. And then finally, all of the remaining vertices are called outlier vertices. They don't belong to any cluster. So that's the definition of the scan algorithm. Let me now talk about the running time or the work complexity of the algorithm. So the work of the scan algorithm is order m times alpha. Alpha is a measure of graph sparsity. It's known as the arboricity of the graph. And m is the number of edges we have in the graph. The value of alpha gets bigger as your graph becomes denser, and it gets smaller as your graph becomes sparser. But we actually have an upper bound on alpha for all graphs. It's upper bounded by square root of m. This is a known fact in graph theory, so we're just going to use that. And therefore, we can upper bound the work of our algorithm by order m to the 1.5, m times square root of m. The most expensive part of the scan algorithm is computing the similarities between adjacent vertices because we have to count the number of common neighbors that they have. We can do this in order m times alpha work using a triangle counting algorithm. And after we compute the similarities, finding the clusters from the similarities is pretty easy. It only takes order m work or linear work in the number of edges in the graph. But because we have this dependence on the arboricity of the graph, which gets worse as your graph gets denser, the scan algorithm is especially costly when you're running it on dense graphs. Another drawback of the standard scan algorithm is that you have to run this algorithm every time you pick different values of mu and epsilon. So therefore, you have to pay order m times alpha work for all the different sets of parameters that you want to try out, which can be pretty expensive in practice. So a couple of years ago, there was work on speeding up the queries for the scan algorithm. So Wen et al. Proposed the GS index, which is a data structure that you pre-compute such that you can take as input arbitrary mu and epsilon values and then output the resulting clusters very quickly. At a high level, the GS index algorithm maintains this neighbor ordering to allow you to quickly find all the epsilon similar neighbors of a vertex. And this neighbor ordering basically is going to sort each vertex's neighbor list in descending order of their similarity to that vertex. Then it also maintains this core ordering, which allows us to quickly identify all the core vertices in the graph. So what it does here is for every possible value of mu, it's going to store a list of the vertices sorted in decreasing order by the maximum value of epsilon, such that the vertex is still a core vertex. And once we have this ordering, then when we're given a value of mu and epsilon, we can now just scan this sorted list of vertices for the particular value of mu, and all of the core vertices are going to appear in a prefix of this sorted list. So to make this more concrete, I'll show an example of the neighbor ordering and the core ordering data structure on this example graph, again with mu equals to 3 and epsilon equals to 0.6. So here's the neighbor ordering. So for each vertex, we have a list of its neighbors, including itself. And then these neighbors are going to be sorted in descending order of their similarity to the vertex. So if we look at vertex D here, I've labeled the similarity of each of its neighbors to D. And we see that they're sorted in descending order. D has a similarity of 1 to itself by definition. And then B has a similarity of 0.89 to D, and so on. And now if we want to figure out all of our neighbors that are at least epsilon similar to ourselves, we can just scan this list from top to bottom until we find a neighbor that's less than this epsilon threshold. So here E is less than this epsilon threshold, and then we just stop there. So all of the green vertices colored here are neighbors that are at least 0.6 similar to the vertex. Then we have this core ordering data structure, which has one row for every possible value of mu. The maximum value of mu is actually going to be the degree, the maximum degree of any vertex in the graph, because you can't have more than that many number of neighbors. And then for each row of this core ordering data structure, we've sorted the vertices in descending order of the maximum value of epsilon at which it becomes a core vertex. So I've labeled these maximum epsilon values on each of these vertices, and let's see how I computed these values by looking at vertex D. So vertex D has a value of 0.77 here. So 0.77, it corresponds to the fact that if we picked a value of 0.77, then D would have at least 3 neighbors that are epsilon similar. But if we picked a bigger value than 0.77, then D is not going to have enough neighbors. Say if we picked 0.8, then D is only going to have 2 neighbors that are epsilon similar to itself, and therefore it can't be a core vertex. Okay, so now with this ordering here, if we're given a value of mu and epsilon, we just go to the row corresponding to mu, and then we scan these vertices from left to right until we get to a vertex with the label that's less than the epsilon threshold that we passed. And we know that that vertex is not going to be a core vertex, as well as any vertices to the right of that. So again, all of our core vertices are going to be a prefix of this sorted order here. So here we have all these blue vertices, which are the core vertices for this particular setting of mu and epsilon. If I changed epsilon to say 0.8, then only B would be a core vertex. All of the remaining ones in this row here have a value less than 0.8. With this data structure, we can now easily generate the clusters for the scan algorithm. So we're going to run a breadth first search or connected components algorithm on the core vertices as well as their epsilon similar edges, which we can easily extract from this index as I just described. So let me now talk about the complexity of the data structure construction. So the work to construct this index is order alpha plus log n times m. So recall that before our scan algorithm had order alpha times m work. Now we have this extra m log n term, and this comes from using a comparison sorting algorithm to sort the neighbors in the neighbor ordering by the epsilon similarity score. And then also we have to do this sorting in the core ordering as I just discussed. The work to query for clusters is just going to be linear in the total sizes of the clusters that are returned. So if we return clusters that are very small compared to the size of the whole graph, then we can actually do less than linear work because we don't have to do any work on the non-epsilon similar edges as well as any of the unclustered vertices or outliers. So the queries using this GS index data structure are fast, but computing the index is slow because this is a sequential data structure. So in our work, we present a parallel index-based scan algorithm, and we show theoretically that it's work efficient. I'll define what this means shortly. And it's also logarithmic span. Again, I'll define this shortly, but the logarithmic span is related to the parallelism in our algorithm. We also propose an approximate algorithm that speeds up the similarity computation using locality sensitive hashing. And then finally, we present optimized multi-core implementations of our algorithm and show that they outperform state-of-the-art scan algorithms. So the model of parallel computation that we're using is called the work span model. The work is defined to be the number of operations used by the algorithm. If you're talking about a sequential algorithm, then the work is just the same as the running time of the algorithm that you might have read about in algorithms textbooks before. However, for parallel algorithms, we also measure the span of the algorithm, which is the length of the longest sequential dependence in the computation. This longest sequential dependence that exists has to be executed one at a time sequentially by definition. So if we have a very high span, then that limits how much parallelization we can get. On the other hand, if we have a low span, then that means that there's a lot of work that can be done in parallel. So we aim to design algorithms that have a low span. We also like our algorithm to be work efficient, meaning that the parallel algorithm has work that asymptotically matches that of the best sequential algorithm for the problem. Because if we blow up the work of our parallel algorithm too much, then our algorithm might end up being slower than the sequential algorithm, even if we're running on multiple processors. So our goal is to have work efficient and low span parallel algorithms. So let me now talk about how we parallelize different parts of the scan algorithm. So first, to find shared neighbors between two vertices, this is done by doing triangle counting because every shared neighbor forms a triangle with the two vertices in question. And then we also add the two vertices themselves to the intersection. And doing triangle counting can be done in order alpha m work and order log n span with high probability using parallel hash tables and existing triangle counting algorithms, which I'm not going to talk too much about. Although this triangle counting algorithm is nice in theory, in practice, it's actually not that fast. So we came up with some important optimizations to make our algorithm run more quickly in practice. So the first optimization is that instead of counting triangles in our undirected graph, we first direct the graph. So every edge now points from lower degree to higher degree endpoint. And then now we're only going to count directed triangles of a certain orientation. And this allows us to significantly reduce the work that we need to perform because each directed triangle is only going to be counted once, whereas undirected triangles will be counted multiple times. And furthermore, this particular orientation allows us to bound the number of neighbors each vertex has to scan by square root of m, which is pretty good in practice. And then to improve the cache locality of our algorithm, instead of using parallel hash tables, which are known to be not very cache friendly, we use a parallel merging algorithm that is more cache friendly. And we need to sort the neighbor list in order to do this parallel merge to identify the intersection of neighborhood sets. Now for computing the neighbor ordering and the core orderings, we can plug in a parallel comparison sort. That's pretty easy. There are a lot of existing algorithms for a parallel comparison sort. However, we had an observation, which is that for unweighted graphs, we can actually use integer sort to improve our work bounds, because integer sort can be done more quickly than comparison sort. So although the similarity scores that we're trying to sort here are not integers, we figured out a way to transform these similarity scores into integers such that two similarity scores with a relative rank before the transformation will preserve their relative rank after the transformation into integers. So this is the transformation we use. I'm not going to prove that this works here, but we discuss it more in the paper if you're interested. After we do this transformation, we can now apply integer sort to sort the neighbors in the neighbor ordering as well as the vertices in the core ordering. And this allows us to get rid of this m log n term. We can either get it down to just an order m term by using a linear work integer sorting algorithm. So this would give us an overall work of order alpha m. However, the span of this linear work parallel integer sorting algorithm is not that great. It's order n to the beta for some small constant beta. It's not polylogarithmic. On the other hand, we can use a integer sorting algorithm that is not as work efficient. It takes m log n work, but it has order log n span. So we have two options here, but for both of the options, the work is still better than the work of the original sequential GS index algorithm. Now for doing queries, recall that we needed to scan these neighbor lists either from top to bottom for neighbor ordering until we find a vertex that's below our epsilon threshold, or for the core ordering, we need to scan it from left to right, again, until we get to a vertex that's below our epsilon threshold. So we do a doubling search where we first check one vertex, then two vertices, then four, and then 8, and so on, until we get to a vertex that's below our threshold. And then we can do a binary search within this last interval to figure out exactly where the cutoff is. And this doubling search can be done in logarithmic span, and it's also work efficient. It's only going to do at most twice the amount of work as the sequential algorithm, because you can only overshoot by at most twice the number of vertices that the sequential algorithm needs to look at. After we find the core vertices and the epsilon similar edges, now we have to run a parallel connectivity algorithm to identify these clusters. In theory, there is a linear work and order a log n span connected components algorithm. In practice, we actually use a more efficient algorithm, which is based on parallel union find. This algorithm allows us to not have to explicitly construct a subgraph to pass to another algorithm, but instead it allows us to maintain the connectivity information on the fly. We also developed an approximation algorithm to speed up the index construction. So the bottleneck in index construction is the similarity computation done using triangle counting. And this is a bottleneck, especially on dense graphs. So we use locality sensitive hashing, or LSH, to approximate the similarity score between adjacent vertices. For cosine similarity, we used an algorithm called simhash, and for Jacquard similarity, we used an algorithm called minhash. The LSH algorithms have this parameter k, which is the sample size, how many samples to take in your approximation. And this parameter trades off accuracy and running times. If you pick a larger sample size, then your accuracy is better, but the running time is worse, and vice versa. So for a particular sample size value k, these are the work and span bounds that we can get. So before we had this alpha term in our work, now we replace that alpha term with a k. And if we pick a value of k that's much less than alpha, then this gives us a significant speedups in practice. And this is pretty easy to do for dense graphs because dense graphs have a large value of alpha. So again, these are two versions of our algorithm, which depend on which integer sorting algorithm we use, but both of them are better than the original algorithm if you pick k to be much less than alpha. We also prove in our paper that if the number of samples k is sufficiently large, then we can correctly classify all of the edges as either above or below epsilon in similarity, except for some small interval around epsilon. We actually found that using this LSH approach was helpful for high degree vertices, but was not very helpful for low degree vertices. For low degree vertices, it was actually better to just scan their neighbors directly and compute the exact similarity scores. So our solution is to only use LSH when we're computing the similarity score between two high degree vertices, and then using the triangle counting algorithm that I described before everywhere else if there's at least one low degree vertex in the pair. Let me now talk about some experimental results. So we ran experiments on an AWS machine on EC2 with 48 cores and 2A hyperthreading. So there's a total of 96 hyperthreads, but only 48 physical cores. The machine had 192 gigabytes of RAM, which was large enough to fit all of the graphs that we tested. We compared our algorithm against state of the art. The first is PP-scan, which is the fastest existing parallel scan algorithm in the literature, developed by Cho et al. In 2018. This is not an index-based algorithm. So every time you want to compute the clusters for a particular value of mu and epsilon, you have to rerun this algorithm. We also compared to GS index, which is the sequential index-based scan algorithm that we parallelized. But there is no existing parallel index-based algorithm, and that's our contribution. So here we're looking at the cost for exact index construction, ignoring the approximation for now. We tested this on two graphs, the Friendster graph, which is a large social network with 1.8 billion edges, and then a biological graph called Cochlea. This is a dense weighted graph. It has 26K vertices and 282 million edges. So this is a very dense graph, which you can tell by looking at the ratio between edges to vertices. In contrast, the Friendster graph is relatively sparse. On the right here, I'm plotting the index construction time on the y-axis in log scale. We're comparing our algorithm on one thread, our algorithm on 96 threads, and GS index on one thread. And for Cochlea, we don't have data for GS index because they don't work on weighted graphs. So we see that first, even sequentially, our algorithm is faster than GS index. So we get a factor of 1.4 to 2.2 times speed up over GS index, even on a single thread. And this is due to the triangle counting optimization that I discussed earlier of directing the graph and then using parallel merging. Although in this case, it's just going to be a sequential merge. And then now if we compare our 96 thread time to our single threaded time, we see that we get between a 23 and 70 times speed up across all of our data sets, which is reasonably good for graph algorithms, given that our machine only has 48 physical cores. We also look at the query time. So here we compare to PP-scan as well as GS index. So for each of these graphs here, I'm plotting the query time on the y-axis in log scale, and then the value of epsilon on the x-axis. And here I fixed mu to be 5, and I'm varying epsilon. This gives us different data points to look at. So the purple line is PP-scan on 96 threads. The red line is our algorithm on 96 threads. And we see that we're significantly faster than PP-scan for all of the different values of epsilon here. And across all the experiments that we ran, we were between 1.26 and 12,000 times faster than PP-scan. And this is because PP-scan requires you to rerun the whole algorithm every time you pass it a different value of mu and epsilon, whereas our algorithm uses a pre-computed data structure every time we want to query for clusters for particular values of mu and epsilon. You might think that this is kind of unfair because we didn't include the pre-processing time. But even if I included the pre-processing time for building the data structure, if we ran at least 10 queries, then our overall time would still be faster than pp-scan. So we're able to amortize this index construction time over just a small number of queries. We also see that we get 5 to 32 times speed up over GS index, which is the single-threaded solution. So this is a pretty good speed up for our algorithm. And then we get even higher speedups compared to our single-threaded algorithm, which has some additional overheads over the single-threaded GS index. That's why it's slightly slower here. Now I'll show you some results comparing our exact algorithm to our approximate algorithm on the same two graphs. And here we're measuring the quality of the clusters using this modularity metric. It's a popular metric that's based on how many edges are within clusters compared to across clusters. I'm not going to formally define it here, but it's one popular metric used to measure cluster quality, and higher is better. And then on the x-axis, we have the index construction time. So for the exact algorithms, we have these solid data points, one for cosine similarity and one for Jacquard similarity. And we only have a single data point because it's an exact algorithm. There's no samples that we need to take. And then for the approximate algorithms, we can generate multiple data points by varying the number of samples that we use in our LSH approach. And for the Friendster graph, we see that the approximate algorithm gives us clusters that are about as good as the exact algorithm. And sometimes it can do this with a lower construction time. Friendster is a relatively sparse graph, so the approximation doesn't give us huge benefits here, although it does give us some benefits. But if we look at the dense cochlea graph, we see that we get huge benefits from using the approximation. So we're able to get clusters of similar quality to the exact algorithm while just taking about 20% of the running time. And this is because the LSH heuristic gives us the most benefits for dense graphs, because in dense graphs, the similarity computation is the most expensive part, and we speed that up using the LSH approach. So in conclusion, I talked about a theoretically efficient and practical parallel data structure for querying scan clusters. Our code is publicly available on GitHub if you're interested in trying it out in your applications. Now I just want to spend a couple minutes talking about some other graph projects that my students and postdocs have been working on with me. So we've been looking at subgraph counting algorithms. In particular, we've been looking at parallel clique counting. So a clique in a graph is a subgraph where all of the vertices are connected to each other. And finding cliques has applications to dense subgraph discovery. So we designed new parallel algorithms for counting cliques and then applied them to algorithms for dense subgraph discovery. And we were able to achieve speedups of up to a factor of 10 over state-of-the-art algorithms, which were also parallel. So here I'm showing the speedups on 30 cores compared to state-of-the-art. Both algorithms were run on 30 cores. And here the value of k corresponds to the size of the clique that we're finding. So we can go up to cliques of size 11 here. And we see that in most of the cases, we get very good speedups over the state-of-the-art. Furthermore, we were able to compute 4 clique counts on the largest publicly available graph, which is a web graph with over 200 billion edges for the first time in the literature. We also looked at cycle counting, which I believe has applications in fraud detection for financial transaction networks. So a cycle is basically a ring in the graph. And we developed new algorithms for 4-cycle and 5-cycle counting in our recent work. 3-cycle counting is actually just triangle counting, and we worked on that many years ago. And again, we were able to come up with parallel algorithms that got orders of magnitude speedups over state-of-the-art. So here are the results for our fastest algorithm on 36 cores over some existing algorithms, as well as other parallel algorithms that we developed. One of the common techniques in both our cycle counting as well as our clique counting algorithms is to compute what we call a low out degree orientation, which takes an undirected graph and generates a directed graph from it by orienting every edge. We actually did this for the triangle counting optimization that I mentioned earlier. And now with this directed graph, we only need to count subgraphs of a certain orientation. And this allows us to significantly reduce the work that's needed to count all of these subgraphs. We've also been looking at batch dynamic algorithms. So these are algorithms for graphs which are changing very rapidly in real time. And when these graphs change, we don't want to have to rerun our algorithm on the whole graph because that could be pretty expensive. And our algorithms are batch dynamic in that they can process batches of updates at a time, which we think is pretty reasonable because in many applications, the updates are coming in so quickly that by the time you look at them, you actually already have a batch of a whole bunch of updates. And if we're processing batches of updates, we can process these updates in parallel. So we designed new batch dynamic algorithms for clique counting as well as K-core decomposition. And we were able to get significant speedups over state-of-the-art implementation. So here I'm showing the running times versus the batch size for triangle counting on the Twitter graph on 72 cores. The red and the blue lines are our implementations, whereas the dashed green and yellow lines are state-of-the-art implementations. And we see that we get significant speedups here, about an order of magnitude. The y-axis is in log scale. And then we did a similar experiment for the K-core decomposition algorithm on 30 cores here. PLDS opt is our fastest algorithm. And this pink line PLDS is a less optimized version of our algorithm. The blue and green lines are existing batch dynamic algorithms. And then the orange and the red lines are actually static algorithms. They just process the entire graph when it changes. And we see that our best parallel algorithm outperforms the other batch dynamic algorithms for all batch sizes here. And then compared to the static algorithms, our algorithm is faster for batch sizes of up to 10 to the 5 for this DBLP graph. And then for larger batch sizes, it turns out it is faster just to rerun the algorithm on the whole graph. So I wanted to mention that we've also been doing some preliminary work on designing parallel clustering algorithms for correlation graphs that are generated from financial time series data. We've been looking at the US stock market data. The data set is actually not that big because there are only several thousand assets that we were able to get data for. So one of the questions that I had, if anyone has any thoughts, if there were larger financial data sets that would be interesting to run graph algorithms on. And then I'd also be interested in learning about other applications of subgraph finding and graph clustering algorithms in financial networks. And finally, I'm happy to take any questions, and thank you for listening.
Thank you very much, Professor Julian. In fact, I have a question.
Yeah, sure.
In terms of your first talk, it was really interesting to me because I've been working with topological features for a while, and of course, working with equivalence relations. In that sense, I've seen you guys have used this whole idea of respecting, of holding properties related to topology. And in my case, I just wonder, what is the potential of parallel algorithms to compute graph isomorphism between graphs?
Yeah. So it turns out that this is a pretty hard problem because it's NP complete. There have been some heuristics that have been done for doing subgraph isomorphism. There's been like a bunch of graph processing systems that are optimized for doing subgraph isomorphism. So you can pass it a small subgraph, and then it can find like all instances of the subgraph. But it only works for small subgraphs because of the basically of the exponential running time of the general graph isomorphism problem. So in the general case, I don't know if there's a good parallel solution, but for special cases where the subgraphs are small, such as the small cliques that we're looking at, or the cycles that we're looking at, then there are some existing solutions. I talked about like some special cases in my presentation, but there are some like more general frameworks out there, although they're usually slower because of their greater generality.
Oh, that sounds really, I mean, interesting. And of course, I suppose that there's like a long path to go, and probably we've got like so many challenges to have such sort of parallelism using graphs and of course comparing graphs. The second question I have is that comes from YouTube and actually from our chat over here. What is the potential you see in topological features when we consider stock market prediction? Do you think we've got like voids and H0 spaces, H1 spaces? I mean, in terms of homomorphisms and of course strategies of understanding recurrences and seasonality in those series?
I see. Yeah, thanks for the question. So unfortunately, I'm not too familiar with the H0 and H1 terminology. But regarding the question about like applying these algorithms to the stock market, that's actually some preliminary work that we've been doing, where we generated this basically this graph that connects like two different stocks if they're correlated by at least some amount based on time series data that we obtained over the past many years. And yeah, it turns out that you can use parallelism to speed up clustering on these graphs that represent stock markets. And although we haven't gotten to this point yet, I know that there have been some other researchers who have shown that you can run graph clustering, certain graph clustering algorithms on these stock market graphs to sort of recover the different industries in the stock market. So that's definitely something that we're interested in exploring more in the future. So basically, like for the parallelization part, we know that we can speed up the algorithm. Now we just need to figure out what is the best clustering algorithm to use and which algorithms will give us the best results in terms of recovering the basically the classification of the different companies.
Oh, quite interesting. I was just wondering if you know the work by Carson and Memoli by Professor Gunnar Carson, and he's been working for a while with clustering stability strategies, and I just wonder. Of course, he's been using a lot of topological features to ensure stability, in the sense that every time we connect vertices, if we've got some sort of small perturbation around a vertex, and that makes, of course, a vertex get closer or far from another one, or from a set of vertices. He's been working in the sense of bringing stability in those scenarios by analyzing some epsilon distances we've got from vertices among vertices. So I just wonder if you had like any prior experience in terms of analyzing stability from your strategies.
Yeah, thanks for the question. So we haven't actually gone that route yet to analyze the stability in existing networks, but actually one of the motivations for our work on the dynamic graph algorithms is actually it makes it easy for us to test the stability, because like basically you just want to make a small change to the graph and you want to see how it affects basically the clusters that you get or whatever other topology you're considering. So one of the big benefits of these dynamic algorithms is that it allows you to easily test this without having to run the entire algorithm on the whole graph every time you want to test this. So I think that basically like one of the applications that we could explore in the future would be to apply these dynamic algorithms to figure out what types of graphs have good stability and what types of graphs don't have good stability, and how we can make modifications to the graph to improve their stability.
Oh, thank you, thank you. We've got an additional question over here. It comes from the chat. What are the properties of graph that makes the algorithm perform better and worse?
Yeah, so for our scan algorithm specifically, it works better for sparse graphs, and it works not as good for dense graphs, because the similarity computation requires you to basically like scan all of your neighbors, and for dense graphs that means you have a lot of neighbors. So that's specific to the scan algorithm. One general property of graphs that affects the performance of parallel algorithms is basically the degree distribution of the vertices. If the degree of the vertices are highly skewed, then this can lead to load imbalance when you're trying to run a parallel algorithm, because some processors will have some very high degree vertices to process, whereas other processors will have low degree vertices to process. And then if they finish early, they'll just be sitting idle. So graphs that have a more uniform degree distribution tend to give us better performance in parallel graph algorithms. For graphs that have a very skewed distribution, we have some ways to make our algorithm still get good speed up, but it requires some additional work and additional overhead. Basically, we partition these high degree vertices so that multiple processors will work on them at the same time, but that has some additional overhead. So having a uniform degree distribution definitely is going to be beneficial to our parallel graph algorithms.
And what kind of application do you believe, real world application, has that sort of power law distribution?
Yeah. So we've looked at several types of graphs. So social networks and web graphs tend to exhibit a power law degree distribution. And then we've also looked at transportation graphs like road networks, and those graphs tend to have a more uniform degree distribution. Like each location is connected to a similar number of roads as other locations.
Oh, nice. And have you guys had the opportunity to analyze the performance according to the power law distributions?
Oh, I don't think we have done a comprehensive evaluation on graphs with different power law degree distributions. There is some theory that we can actually write down that like expresses the running time or the work of the algorithm based on this power law degree exponent. But in terms of experimental work, we haven't actually done that. And that might be an interesting thing to consider in the future.
Oh, thank you. Thank you very much, Professor Julian. We have no more questions, but of course, it was an honor to have you with us. And I suppose people are going to keep in touch with you and send questions later, probably. Thank you very much for presenting such very interesting work.
Yeah, feel free to send me an email if you have any questions. I put my email in the chat. I'm not sure if the people on YouTube can see it.
Yeah, maybe not, if you allow me, I can pronounce it here. Yeah, maybe.
Oh, yeah, sure. Yeah.
Yeah, the email of Professor Julian is jshun@mit.edu. Thank you very much, Professor.
Yeah, thanks a lot, Rodrigo, for inviting me, and yeah, thanks to everybody here for inviting me and listening to my talk.
Thank you, thank you. Now we go for our next talk, and we have Dr. Homa Esfahanizadeh. I'm not sure if it's right, the pronunciation, sorry, Homa. It's really great to have you here, and it was really pleasant to read your work. And I hope to have like some very interesting questions at the end. Thank you.
Hello, everyone. Thanks for the nice introduction, and thanks for having me today. So you have my screen, right?
Yes, it's perfect. Yeah.
My name is Homa Esfahanizadeh, and I'm very excited today to share with you our recent work on training sensitive data securely. In this project, I had the pleasure to work with a great team. They are Adam Yella, Rafael de Oliveira, Professors Ken Duffy, Manya Qobati, Tommy Yakola, Vinod Vaikontanathan, Regina Brasília, and my advisor Muriel Medard. I would like to start with the problem itself and its importance. In emerging ML applications, so the data owners would ideally like to outsource their data to the cloud for an ML developer to train a machine learning model. Why is that? For two basic reasons. First, data owners do not always have the compute resources to train, and more importantly, usually high accuracy training needs sufficient and diverse data from multiple data owners like banks and financial organizations. As much as the sharing is important for these reasons, data owners usually are not allowed to do that because of privacy, business competitions, and basically what we call privacy and security reasons. It brings up the necessity of a methodology that allows the data owners to privately share their labeled data for a classification purpose. Let's take a look at the problem. The solution for this problem. Ideally, if there was a method for the ML model to be trained on encoded data that only allows leakage of information as much as needed for classification, that would be perfect. There have been some works in the recent years on this problem. They are majorly go into one of these categories, homomorphic encryption or differential privacy methods. In homomorphic encryption, it is like a basic, it is a very rich direction, but recently have been used for training ML models on encrypted data. What are the problems with these methods? First, they are computationally very expensive. They require communication overhead. They need changing the ML models because of the nonlinearities of the activation. And at the end of the day, they usually lower the accuracy. The second method, the standard differential privacy method, they usually add a noise to the system to make sensitive samples statistically indistinguishable. But most often it comes at the cost of lowering the accuracy. What we are interested, the goal is the same, but we want a computationally light encoding scheme that doesn't affect the accuracy, the utility of the trained ML model. Briefly, the contributions of our work is digging into the problem, presenting a theoretical framework for privacy and learnability in such setting. We propose an encoding scheme with an architecture motivated by the theoretical guides. Also, we empirically examined the robustness of our encoding scheme against a set of attacks. So, briefly speaking, our approach is this. We have a family of encoders. The data owner randomly picks one function from this family and encodes its data using this function. But the word outside the data owner does not know which of these functions have been selected by the data owner. Specifically, our encoding scheme, which we call NeuroCrypt, is based on using deep neural networks for constructing this family of encoders. Because consider deep neural networks, the weights can be chosen randomly. What weights has been chosen is like a key that only the data owner knows. So briefly speaking, we pass each training sample in the data owner. We pass each training sample through a random deep neural network, and we publish the labeled encoded samples for ML developers. Here's the privacy problem. This Alice, Bob, and Eve are famous for privacy problems. So the data owner, because our experimental results are for a medical setting for now, as like the toy example, I used chest X-ray images to show the importance, because there are many privacy concerns regarding sharing the patient data. So the data owner, in this example, a hospital, has some sensitive data. It uses our approach, NeuroCrypt, to form encoded samples. They are not familiar with human eyes, and publishes the labels associated with this encoded for Bob, the ML developer. But ML developer would use it for classification, training an ML model. But there is an adversary that is interested to identify information beyond this purpose. This motivated us to define perfect privacy for this setting. We say an encoding scheme is perfectly private if a computationally unbounded adversary who observes the label encoded dataset and also has access to some helpful information, some other chest X-ray datasets that are public on the web, cannot infer information about the sensitive samples beyond what could be inferred only by observing the labels. So this is the problem. Now we are ready. As first step, we theoretically explored the problem and what we can expect, basically. So the first question is if perfect privacy and perfect learnability if it is achievable. The answer is yes, and we came up with a theoretical family of encoders that provide both perfect privacy and perfect learnability. The encoding scheme is this. Suppose this is the universe of all possible samples. For example, in case of the medical datasets, one family that people at chest X-ray is diagnosed with pneumonia and the other one normal. If we want to encode a sample with label I, we randomly replace it with another sample in that class. So intuitively, it makes sense that the adversary does not know anything other than the label, because we only know the encoded sample and the original sample. They only share label. So also because it doesn't change the label structure, this scheme, which we call ideal family of encoders, achieve both perfect privacy and perfect learnability. At the first glance, it may seem that the described ideal family of encoders require the full knowledge of labeling function. Although it might be the case for some examples, here we show a counterexample that this is not true in general. So let's take a look at some example of data set and classification purpose that we can implement the ideal family of encoders without need to know the label of the sample. Suppose like the sensitive samples are binary vectors, and their label is the number of entries with value 1. The encoding scheme is a random permutation of this vector. As you see, like the random permutation does not change the number of entries with value 1. So the labeling is invariant with this encoding. So for sure, the random permutation encoding does not change the learnability. As when we permute, only the location of elements change. So basically, it only maps one vector in a class. A class is all vectors that have the same number of entries with value 1, with another sample in this class. So this is one example that the ideal family of encoders is implementable without need to know the labeling function or the label of the samples. That was like some kind of achievability. It is like the Shannon encoding because the Shannon achievability results was like there is something there. The capacity was there. So it showed. He showed that it is achievable, but there was work later to show coding that asymptotically achieved that bound. So this is a motivation for us. We should come up with coding schemes that gets us closer to this perfect privacy. But achieving perfect privacy is often impractical or very difficult to do. So we introduced in our paper a weaker notion of privacy, and for that we introduced a tool which we call LC anonymity list. The LC anonymity list is a set of functions in the family of functions that the data owner chooses from. It is a partitioning of that family of encoders. The LC anonymity shows all possible encoders that the data owner might have used to encode its data based on the attacker's site information and observations. LC anonymity list by itself gives us a set of plain text for an encoded image. So it is like k-anonymity. Using this tool, we can say that, okay, from the view of the attacker, the original sample for this encoded sample is this set of possible plain text. So if the confusability is the whole class, it is the ideal family of encoders. Like seeing one encoded sample, the attacker cannot say anything. They cannot restrict the members in the class further. But it is usually hard to achieve. The LC anonymity is like some kind of partitioning the members of each class. In practice, these partitions have overlap with each other and overlap across the class, but it is for just a visualization and see what happens if the perfect privacy is not achievable. We get something very similar to k-anonymity list in the literature. I remind that Alice, the data owner, randomly chooses an encoder from a family of encoders. So the design of an encoding scheme is basically to construct a good family of encoders. We have some nice insights from the theory that guided us to come up with the architecture of NeuroCrypt. One thing is like just extending the family of functions that the data owner chooses from does not provide better privacy. We basically have an example that adding a member to the family of encoders from which the data owner samples from might potentially hurt the privacy. So just extending the family is not the solution. However, we have these nice results that composing family of encoders can only preserve or increase the privacy. So if you look at like a deep neural network that we use for encoding, different sequential layers are mimic this functional composition. And this was the guide for us to come up with the architecture of NeuroCrypt. So we leverage our theoretical results and function composition to use deep neural network for encoding our dataset. So this is the architecture that we use. It is a convolutional neural network. Why we use convolutional? Because we are considering the image classification, and there are works that shows convolutional neural network is good for labeling these classes. For us, it showed us that it preserved the learnability, and like for this example, the results that I show later, we proposed an architecture that consists of convolutional layers with non-overlapping strides. batch normalization, nonlinear activation functions, and a random positional embedding. So I just want to remind that there is no training in encoding for privacy. This is like inference with a random network, with a non-trained random network. So it transfers this sensitive sample to an scrambled image that it is not human friendly. Besides, we show that it is at least very difficult to break. Now let's take a look at some empirical results on the utility of the models that are trained with our encoded data. In this setting, we have two benchmark data sets of chest X-rays. One is a mimic, what is called in the literature mimic data set. It plays the role of hospital 1. The other one is Checkspert. It plays the role of hospital 2. So we have two hospitals. Each one has its own data set of chest X-rays of its patients. We evaluate the ability of the ML models to predict 5 different kind of abnormalities that is listed here. All images are downsamples to be grayscale and the same size. What we do, we compare the performance of NeuroCrypt-based models to predict these abnormalities to a standard architectures trained on original uncoded images. We have two settings, single institution setting and multi-institution setting. In the single institution setting, the machine learning model is trained with the data of one hospital. In multiple institution setting, it is trained on the combined data set of two hospitals. The second multi-institution setting also has two categories, what we call combined clear and what we call combined private. The first one, combined clear, it means that we have one encoder. It is a random deep neural network. It is being used for both hospitals. So it is kind of the hospitals are in sync with each other. They trust each other because they use the same encoder. The second, combined private, it is much more interesting because it doesn't require the hospitals to trust each other. So each hospital uses its own realization of the random deep neural network to encode its data. Let's take a look at some interesting numbers. The model that we are using here is VIT because it is not sensitive to the order of patches of an image. So this is the first model that is trained using the original data of hospital 1. It is the first abnormality, second abnormality, but I want to attract your attention to the last column that shows the prediction accuracy, AUC, average over all these 5 kinds of abnormalities. When the model is trained using original data of hospital 1, we obtained AUC 80. When the VIT is trained using our NeuroCrypt encoding scheme, is trained using the encoded data using our encoding scheme, it also achieved AUC 80, which means that we didn't hurt the accuracy. We repeated this experiment for the original data led to AUC 77. But when we use the NeuroCrypt encoded data, we even achieved a bit higher AUC. We generally do not claim that encoded data, it is counterintuitive, but we generally don't claim this might happen a lot. But there's a justification that human-friendly representation is not always the best representation for training ML models. Sometimes it causes biases or other problems. Actually, there are works that adding some noise or perturbation can improve the accuracy. We believe what happens here is in the same line as this line of works that say that some kind of perturbation might actually help. This slide is about the multi-hospital setting. I want to check the timing. It is the multi-hospital setting. So let's consider combined clear setting. Both hospitals use the same encoder. When we train the ML model on original data, but from both hospitals, we got AUC 82. It is a little bit better than both 80 and 77 because it is more diverse, richer data set. So it makes sense. When we used one encoding scheme for encoding the data of 2 hospitals, the AUC was 83. It is almost the same, a little bit better for the same reason that I talked about. And the last row shows when each hospital uses its own random encoder to encode its data, but still we trained the ML model on combination of the data of both hospitals, we achieved AUC 82, which is the same as like the first row when there was no coding. So I want to remind the storyline. We theoretically analyzed the problem itself. We found an existence results. We were motivated by our theoretical part about function composition to use deep neural networks for encoding a scheme. We developed this, but it didn't hurt learnability in our setup. However, for showing the privacy preservance of this encoding scheme using LC anonymity list, one needs like many information and unlimited, a very large computational resources. It is often impractical. So alternatively, we evaluated the privacy of NeuraCrypt architecture by empirically measuring its robustness against attacks. So for now, we have tested 2 kind of attacks, GAN-style attacks. And also we have a public data set on the internet, and we encourage participants to come up with attacks on our proposed NeuraCrypt architectures. You can find it as NeuraCrypt challenge on the web. The 2 attacks that our team has tried, we call the first one Adversarial Attack, and the second one transfer learning attack. And we have some measure to quantify the success of this attack. Let's take a look at each one of them separately in the next slides. Our first attack, Adversarial Attack. The attacker in this attack aims to approximate the encoder that is used by data owner to encode the data. The attacker here uses some kind of GAN-style attack. Suppose the attacker has some public data set. Let me annotate here. So this is the encoded data set Z that the attacker has access to. It is labeled encoded data. It is the chest X-ray data set of a hospital. Sorry about that. So I'm not very successful with using annotations. So the attacker has also access to a public data set that has the same distribution as the original sensitive data sets. So the attacker tries to train a NeuraCrypt to approximate the encoder, tries to train a deep neural network to approximate the encoder that is used by the data owner. It trains it such that the distribution of the encoded data has the same distribution as what has been observed as encoded data. So let's call this encoder T star that the attacker has found using some kind of GAN-style attack. So we do some kind of normalization for brevity. I don't talk about this normalization. It is just helpful to find how good is this approximation. NeuraCrypt is our architecture that is based on deep neural network. Linear is a very simple 1-layer encoder without any nonlinear activations. Its purpose is like to show linear random encoders are not sufficient for providing privacy. As the success measure, we use a mean square error, MSE, between the generated ciphertext Z star and real ciphertext Z. When we measure this if this MSE is 0, it means that the attacker accurately could break the encoder that was used by the data owner. When the attack was applied to NeuraCrypt, the success was 4.44. And when it was it was applied to linear, it was 0.43. So the MSE is much lower for linear than nonlinear. Our intuition is basically linear scheme cannot provide privacy. Our several experiments show that they can be broken easily by GAN-style attacks. And it is the same reason as a similar work that is called Instahide, like 2 years ago, was broken right after it was published because it was based on linear functions. Can you hear me? I have some difficulties.
Yeah, Homa, we can hear you. What happened?
Can you stop sharing because I cannot go to the next slide? If you can help me to, I don't know what happened.
Let me see if we can help you.
Okay, great. Let me see if I can do it again. Okay, great. So I don't annotate anymore. Thank you very much, Ethan.
Let me just see that if the YouTube is seeing the same slide. Oh, yeah, you're online. Go ahead. Thank you.
You're good? Okay, great. Yes, I was not able to go to the next slide. Thank you very much. So this was our first attack that showed NeuroCrypt is much stronger than linear competitives against this kind of attack that try to break the encoder. The next question is very interesting. What happens if the approximation is just good enough to find another sensitive attribute about the encoded data? Suppose like the encoded data is like if this scrambled image has pneumonia or not, but the attacker wants to try some sensitive information like if it is from a specific hospital or if it is female or male, some sensitive attribute. So it is a security leakage. So the attack is, we began with the best estimated T-star from the previous attack, the T-star that was supposed to be T, but it is a bit different from T. We built a new classifier using this T-star. How we do that? So we have this T-star. We have a public data set like X. We encode this public data set using this approximated T to form another encoded data set. But now we can associate it with some other sensitive labels like gender. Here, I think it is like for predicting edema. However, the sensitive encoded data was only had label cardiomegaly. Then we used this classifier to classify the original encoded data to find the sensitive attribute. So when we used NeuroCrypt for this purpose, the AUC was close to 50. It was 52 plus minus 4, which means that we were the attacker was not successful to classify for this attribute. But the linear scheme, the AUC was 86. It is pretty high. Again, showing that NeuroCrypt was doing much better than the counterparts. As I said before, we also have a public challenge data set on the internet. We encourage everyone to take a look and to come up with attacks that also encourage us to come up with better NeuroCrypt architecture. We have two challenges. One is like a baby challenge. It is our initial step. We provide two data sets, both original data set and encoded data set. But the mapping is not known, which encoded sample is the encoding of this which plain text. The mapping is unknown, and the participants need to find this mapping. In reality, the attacker doesn't have these matching data sets. They only have some encoded data set and some public data set. So it is not directly under our threat model, and actually it is recently being solved by a group led by Google. You can find more information here. They have an archive paper on this challenge. Our second challenge, we only provide the encoded data set, and we tell people this is a chest X-ray data set. And the participants are free to use any kind of public data set. And this challenge is not yet solved. One of our ongoing work is estimating the security leakage using information theoretic measures. Like the LC anonymity list, finding the mutual information analytically is very difficult. But we know that the mutual information of the plain text and the ciphertext, given the label, is a good measure of how much security leakage is there. So we are developing a scheme to predict this mutual information, to approximate it, to use it to improve our architectures. To this, we use a classifier to decide how likely two images are a plain text ciphertext pair. We train this classifier across many encoders and plain text. It is some kind of a loop between attacker designer. Attacker tries to attack the designer, uses the score to improve the design. In summary, balancing the needs for privacy and learnability, the predictive utility of ML models is a central challenge for machine learning in sensitive fields like in medical fields, in finance. So what we did, we proposed a theoretical framework to characterize the privacy of an encoding scheme where the data owners randomly pick an encoder from a rich family of functions. We showed the existence of an encoding scheme that provides both perfect privacy and learnability. It is like an existence results because in practice it is usually hard to be implemented. Motivated by the theoretical framework on function composition, we proposed a deep neural network-based encoding scheme that we called a NeuroCreep, and we performed empirical analysis of its utility and privacy using some GAN-style attacks. As future work, I would like to invite our partners from industry, if they're interested, to give us other interesting data sets. We use deep neural networks as convolutional neural networks because the data set, because it was supposed for classification of images. We believe if it is text or if it is voices or other type of data sets, we probably need to come up with other encoding architecture. So it would be super interesting to explore other applications as well. And as I said, one of our ongoing work is using security leakage estimator to improve the architectures. Like, should we use ReLU? Should we use TANH? What kind of architecture? How many layers? These kind of questions. We are also extending our theoretical analysis using the guesswork techniques to quantify exactly how two encoding schemes are comparable to each other. The guesswork says that how many guesses it takes for an attacker to find the original data or the encoder. So it is a solid ground to quantify the privacy. With that, I also want to thank the great team that I've been working on from MIT and Maynooth University, our sponsor FinTech at CSAIL. And I think that's all. Thank you very much for your attention. If there is any question, I'd be happy to take.
Thank you, Homa. Amazing presentation. Thank you so much for being here in this afternoon. First question, sorry to ask that, but how can I pronounce your name? It's Homa?
It's Homa, yeah. You did well both in my name and last name. Thank you.
Okay, thank you. So Homa, thank you for being here. I think that we can start with some questions. We have 2 or 3 questions, okay? And yeah. I will be the first. I will do the first question for you because I think that this trade-off between privacy and using data from our customers to have better products to offer to them is something very, very important for us. And now and at Itaú, we are keeping the security and the privacy in the high levels in the last decades. And with the new regulations, such as the GDPR and the LGPD in Brazil, this is even more important, So this kind of work is very important for us at Banco Itaú, And my first question is about the reason that you choose the deep neural networks. Can you give more details about what motivates you to approximate the encoder space using deep neural networks, and why this approach performs better than other techniques?
This is a great question. So at first I want to start that this is a new problem. It is like this, the last 2 or 3 years, people have considered training on encoded data, particular encoded data. So the last, why we use deep neural network, it was from a couple of intuition. One was the function composition that shows that theoretically, if we make the neural network deeper, we can improve the privacy. So, and we said that if we saw that if the architecture is right, it doesn't hurt the learnability, at least notably, like using using the AUC metric, or like in the examples that we considered. Also, the deep neural network have, when the weights are chosen randomly, provide a high amount of entropy, which can make the brute force attack very difficult. I agree that the privacy is very important. So for now, we are encouraging for people to try to break our approach. It is like the other way around. We have initiated some attacks, and we also asked people to try to attack it. We are exploring the theoretical guarantees more, but it is like based on if it is broken or not yet, basically.
Yeah, I think that you mentioned about this. You are inviting people to attack your solution, your proposition. So this is related to another question that I have. It's about the work about us using this work in the future. Can you explain how or if we could test the neural encryption in production data? And what are the next steps of your project? I understood that the next steps of your project are the attack. You are inviting people to test. But how can we, for example, test this in production data, for us at Itaú? Or do you think that it's not safe for now to use the neural encryption?
Yes, actually, our next step, to extend this work for other kind of, not computer vision, maybe NLP, other kind of setting, or like just other data sets, not medical data set. If there are some kind of data sets that you can share, or like the partners that is safe to be shared with MIT, to work with, I think that should be super interesting to see, at least to start with considering the utility of the trained model. So we are encouraging people, and we have a team that are developing it. We have hired a person to actively work with these attacks. It is not just because to see if it is broken or not. If it is broken, there is a reason. One of our initial architecture is because we used ReLU as activation as nonlinearity, but ReLU is basically piecewise linear. So it was a flaw. So we learned from the attack and improved our. So for coming up with a solid protocol for encoding, I think this kind of attacks and encouraging people to attack would give us clue to improve our design. Also, we are using some kind of very fun estimator to basically quantify how much the original data and encoded data are correlated. That would be an indicator of the security leakage. It would be like a scroll down button to show how much security. So it probably at some extent, if the security leakage is very low, it affects the learnability. So it would be the designer choice. In this spectrum, what would be the safe way that they're comfortable with?
Yeah, it is the trade-off between security and, in this case, the utility of the model, right?
Exactly. For now, we even reached to the trade-off because training a model is so low influence. It requires so little knowledge that losing all this distortion didn't affect that. But if we increase the distortion after some point, it should affect the learnability, and that would be the part that this trade-off appear.
Thank you. We got some questions from the audience. I will start with my questions. Maybe we can talk more later, because this work is very related to some works that we are developing in our laboratory here in Brazil. In Brazil, not here because I'm in Boston, but in Brazil. So maybe we can work together to share data. Maybe let's see if you can work together to share. Yeah, let's see.
Yeah.
So we have some questions. Let me just get one. It is from Andre from our lab. It's are there guarantees that the resulting encoded data of neurocrypty will carry the same information for any application? So are there guarantees that the resulting encoded data of the neurocrypt will carry the same information for any application? For example, you are testing the data with medical data. Can you guarantee that this encoded data, the result of the encoding, will be the same for any kind of application?
Thanks for this question. It is an interesting question. I have two points here. One, a neurocrypt architecture is evaluated for a purpose. For example, we can say that this is good for encrypting chest X-ray images of this of this size with and their grayscale. So if there is any other application, it needs to be designed to make sure that at least empirically it shows comparable predictive utility with the time that the model is trained with original data. The second is like the interpretability of the data. It is correct, the encoded data that for sure does not carry the same amount of related information compared to original, but we cared it actually should carry only the amount of information that needed for a training classifier. So as long as we can train a classifier with a good precision that is tolerable for the user, it should be fine. And that is the purpose of privacy, to actually lower the information that is not needed.
Got it. I think that this is related to the second question from Andre. It's about, should you choose the model's architecture according to the type of application? So I think that you answered that, right?
Yeah.
Go ahead.
We use convolutional neural network just because it is computer vision, it is image classification. Probably if it is some other, maybe just dense neural network or NLP models. So it is for this kind of data sets that we have explored so far, and it is interesting to consider other type of random models for encoding.
Yeah, got it. So we have more questions. You are popular. Wait, you're. Thank you. It is from Flavio Nakasato. It's also a researcher from our lab in Brazil. So thank you, Homa. Since much of the company's data is tabular, like SQL or and other related databases, what are the main challenges in adapting these systems to it? I think that, go ahead.
Can you clarify more, like for other type of data sets, right?
Yeah, because if I understood right, we are using this model in images, right? For example, if you are using a SQL database with another kind of data, for example, text, there's some challenges in adapting your model or not?
So it is challenging because we are actually designing our encoder architecture. The weights are chosen by the data owner, but the architecture, it is our design for computer vision for now, image classification. For sure, if there are other data sets, we should come up with other architectures that preserve the learnability. So this is our ongoing work and a very interesting direction to pursue in the future.
Got it. Great. So let me see if you have more questions. Okay, so we don't have more questions for now, I think. And so if you have another point, if not, thank you so much for your presentation, Homa, to be with us this afternoon. It was so kind to accept our invitation. Thank you so much. I think that we have some common interests, so maybe we can work together in the next steps of your project, right?
Yes, of course. It was my pleasure. Thanks for having me. I look forward to more discussion offline and possible collaborations. Yes.
Great. Thank you so much, Homa. Now we will start for the next point, which will be the finish this workshop. And thank you for our audience also. Okay, I will continue in Portuguese. Sorry, but thank you so much.
Thank you very much.
Okay.
Bye, everybody.
Ok, thank you. Bom, pessoal, com a apresentação da Homa e do Julian, eu acho que a gente vai chegando ao final desse workshop. Esse é um workshop científico, como vocês puderam perceber, foram apresentações extremamente técnicas, e esse é o objetivo desse workshop. Fica de novo o convite. Eu acho que a gente tem... Levi, você pode compartilhar, por favor, a apresentação? Isso. Fica também o convite àqueles interessados em alguma vaga no Itaú, em tecnologia. Nós temos vagas para cientistas de dados, que estão publicadas no site, na 99 Jobs. Fiquem à vontade para usar esse QR Code para acessar essas vagas. A gente vai oficialmente encerrar o evento, e eu vou estar por aqui com mais algumas pessoas, caso vocês tenham dúvidas sobre o Itaú, sobre o C2D, e ficamos à disposição. Agradeço a todos a participação. Encerramos aqui o evento e estou aberto para perguntas. Muito obrigado a todos. Perguntas via chat no YouTube.